Warning, the video you're about to watch contains mathematics at the level of college algebra and trigonometry. All material has an assumed prerequisite of both Algebra 1, which is elementary algebra, and Algebra 2, which is intermediate algebra. While some prerequisite topics are reviewed briefly, a more thorough review of these entrance topics can be found by searching the web.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes.
Hello, my name is Roy Simpson, professor of mathematics at Cosumnes River College in Sacramento, California. This video is actually a really good video to watch because you're going to be using in a pre-calculus course some type of graphing technology to investigate graphs before you go into calculus. You need to really understand how technology and graphing go hand in hand. And you may already think like, don't worry, I know how to use a graphing calculator or something like that. Well, that's not what I'm talking about here. I'm really talking about like specialized graphing techniques. So I want to showcase how to graph stuff like this using something called Desmos, which you should probably already know about. It's not that big of a deal. It's a very popular program. So let's go ahead and hop over to Desmos and graph this piecewise defined function. I just want to showcase how that's done so that you can do it when it comes to homework problems in your class. And you can always surprise your instructor. Oh, this is how you graph a piecewise defined function in Desmos. Most people do not know how to do that. So let's go there. All right, so we're over here in Desmos. And the first thing that I tend to do when working in Desmos is really just some cleanup. I turn off the grid. Sometimes I'll go to reverse contrast because this might be easier on your eyes or something like that. And if I'm recording a video, I put it in projector mode just so that everything's a little bit easier for you to see. I think in this case, I am going to turn on reverse contrast for no other reason than to show you that, well, you can do it. Now, the goal in this part of this video is to showcase how you would graph a piecewise defined function in Desmos. Pretty darn easy. And the function we are graphing is x squared if the absolute value of x is less than or equal to 1, and 1 if the absolute value of x is greater than 1. So I'm going to create a function. And then once you have the function name going on, you put braces. Just like you would with a piecewise defined function. A piecewise defined function has that single left brace, and then you split it into two cases. Unlike a written piecewise defined function, however, Desmos requires you to put the domain restriction on each piece before you put the actual function. That is, if we wanted this function to be x squared when the absolute value of x is less than or equal to 1, we would have to actually write that in reverse order. In other words, we want the absolute value of x to be less than or equal to 1. So that's our domain restriction for our first piece. And then you put a colon, and then you write the function for that piece, x squared. The way you could read that is, if the absolute value of x is less than or equal to 1, then the function is x squared. And you can see it over here on the right-hand side. Then you put a comma for the next piece of the piecewise defined function. Whenever the absolute value of x is greater than 1, our function will be 1. So I'll put a little colon here and I'll put a 1. And now we have our piecewise defined function written beautifully or shown beautifully within Desmos. And that's how it's done. And you can do this if you have 3 parts to this, you can continue on with that. So piecewise defined functions in Desmos, not bad. The only thing that you really can't do with piecewise defined functions is show the open or closed holes. For example, let's suppose that instead of being x squared when the absolute value of x is less than or equal to 1, it is 2x squared. Now, if you take a look at that 2x squared, it's supposed to be 2x squared for x less than or equal to 1. And it actually is 2x squared for x less than or equal to 1. You can see it right there. However, it's supposed to be y equals 1 when absolute value of x is strictly greater than 1. That means when x is greater than 1 or less than negative 1. But it doesn't have the open circles down here. So you could include those manually by doing the following. So I just typed in the point, and then you can go up to edit list And if you click on that, you can change it to an open circle manually and change its color if you want to, and then just click done and you'll see you have an open circle there. It's not something that I would actually have my students do, but I'm just letting you know that's something that you can do. You can create the open circles and actually solid dots. For example, if I want a solid dot up at the top for that middle function there, at -1, 2, I would just go ahead and edit list. I'd probably create the same color here. It's already solid dot and that's it. I'm done. So that's graphing piecewise defined functions and showcasing the open and closed circles. All right, hopefully that was pretty good for you. I'm glad that we actually were able to do that. Now let's talk about one of the most essential functions that you'll find in differential calculus. So you find that here, but it's very useful in differential calculus. It's also used in other places, but differential calculus, this is where this function sings. It's called the greatest integer function, and it's written as f of x is equal to a double bracket of x. It almost looks like an absolute value. If you're gonna write it by hand, it looks like this. F of x is equal to, and then you got a bracket, like a square bracket, but with 2 pipes on it rather than 1. And this returns the greatest integer less than or equal to x. So let's actually play with this function first, because it is a very powerful function. So for example, f of 1, well, that is written this way, right? So you just plug 1 in for x. Now what it's going to return is the greatest integer less than or equal to that 1. Now let's just look at a number line. Here's the number 1, and I'm going to start looking to the left on the number line, but I start where I'm standing. Okay, I'm standing at the number 1. You're allowed to look where you're standing first. So if you're standing on an integer, which 1 is, then that's the answer. That's the largest integer less than or equal to 1. Where it gets interesting is if you have something like, oh, I don't know, let's say 3.14, very popular number. So f of 3.14 is the greatest integer function of 3.14. Now pretend as though you're standing on this number line at 3.14. You're standing right there. And you have to look to the left. You can look at your feet, but that's not an integer that you're standing at. So you look to the left, and the next integer in line just to your left is the number 3. So that's what this would return. If you're into computer science, this is called the floor function. What's very confounding to a lot of students is when you get into negative numbers. So if I told you I want you to evaluate f at negative, let's do negative 1.9. Well, that's the greatest integer of negative 1.9. Let's pretend as though you're standing at negative 1.9. Here we are, we're standing right there. But you can only look to the left or down at your feet. Well, down at your feet, that's not an integer, so you can only look to the left. The next integer to your left is not negative 1, it's negative 2. That usually throws people off. So it's the greatest integer less than or equal to the number that's inside the argument, or that acts as the argument for the greatest integer function. This is a really, really cool function, and you can actually graph this in Desmos. So let's go ahead and go over to Desmos and graph this function. Now there are several ways you could try to graph this function. Probably one of the ways that is going to be the longest, in fact, not probably, definitely the way that is the longest, is to try to build a piecewise defined function. That is, we start with f of x is equal to and then a brace, and we know that the function will return, for an example, the value of 0 if x is greater than or equal to 0 but strictly less than 1. So there's our domain restriction. X is between 0 and 1, including 0 but not including 1. And we know that the value of the function in that interval will be 0. And we know that's the value of the greatest integer function in that interval because if x is between 0 and 1, well, the largest integer less than or equal to x would be 0. If you're standing at x equals 0, well, again, the largest integer less than or equal to 0 is 0 itself. But what happens if x is between 1 and 2, where we get to include 1? Well, that would be this condition right here. And we'll go ahead and use the colon to add on a function there. And the value of our greatest integer function in that interval is going to be 1. Now again, I just want to reiterate that Desmos is not going to do the solid dots and the open circles for the edge cases here. That's just something that it will not do. You can manually place those in there if you want to, but it's going to be a lot of work. So we can continue to build this greatest integer function by going to the next interval from 2 to 3. And we know on that interval, the greatest integer function is going to be 2. And you can see this step pattern going on. This is why they call it the step function. But luckily, there's a faster way to get Desmos to graph this step function. I mentioned it earlier that if you're into programming, you already know from programming that there's a floor function. Well, it turns out that Desmos also contains this floor function. You would just type f of x is equal to floor of x, and there you have it. Very fast and beautiful, and really showcases very quickly the step pattern that the greatest integer function has. As an aside, you could be asked to do manipulations on these types of functions, for example, transformations. If I wanted to take this floor function and maybe add a half to it, or well, in this case, because my fingers touch 2 buttons at once, if I want to add a 0.65 to it, it'll lift up the greatest integer function by 0.65 units. If I want to, let's say, subtract, let's subtract 5 from the inside of the greatest integer function, it shifts the entire function 5 units to the right, just like you think it should. If you were to multiply the front end of the floor function by, let's say 3, it then makes everything 3 times its original height. That's kind of harder to see in this case because at 0.65. So let me take off the 0.65 so you can actually see it. And it's probably easier even to see if I just move it back to where we're centered at the origin. And you can also do things like what is -3 of that, and it does the same thing that you think it should. It rotates it about the x-axis. So this type of function also follows the patterns of transformations. You can apply transformations to this type of function. Everything works like you think it should. Now, before we get too far, we're going to list out some definitions because in a section called Graphs of Functions in a textbook for Precalculus, often they have a lot of extra information. I want to talk about that information briefly. A lot of it is very, very obvious, but still it's good to talk about it. The precision of the definitions that I write down reflects the rigor we need to attain in our journey through mathematics. I'm just reading this off my page here. Moreover, these definitions are vital in calculus. And you could ignore my mention about subsections and stuff like that because the reality is you might not be using the book that I use. So I'll just remove all that stuff and get it out of there so it doesn't clutter your page. Starting with the idea of an increasing or decreasing function. Now, you know naturally from dealing with graphs all the way through algebra that a function is increasing if it's rising from left to right. That's an increasing function. And you know a function's decreasing if it's falling from left to right. But those are very loose definitions and honestly not rigorous at all. These are what I would call layperson definitions. It's sort of like when somebody says, oh, the color green is, the combination of yellow and blue. Well, that has a semblance of truth to it. There's actually a better definition. You could say like the color green is this wavelength on the spectrum. That's what we define the color green to be, or something like that. You could be very rigorous with the definition rather than just being like, oh, yellow and blue make green. So that's what we're going to do here. We're going to be a little more rigorous. So a function f is said to be increasing on an interval, and we call that interval I, if f of x sub 1 is strictly less than f of x sub 2 whenever x sub 1 is less than x sub 2. Let's visualize this. As long as x sub 1 is less than x sub 2, then we would say the function is increasing if f of x sub 1 is less than f of x sub 2. And x sub 1 and x sub 2 are arbitrary. This would have to hold for any combination of x1s and x2s on some interval that you're saying your function's increasing over. A similar definition holds for decreasing. A function's considered to be decreasing if f of x sub 1 is strictly greater than f of x sub 2 for all x values in your interval whenever x1 is less than x2. So again, going over to our decreasing function and kind of highlighting this, suppose that you have 2 points, random by the way, arbitrary points, and one of them is less than the other. So x sub 1 might be less than this x sub 2 right here. This function is decreasing on this interval from here to here, let's just say, if no matter where we choose x1 and x2, as long as x1 is less than x2, then it's considered decreasing if f of x1 is greater than f of x2. This level of precision in language is what you have to get used to as you move forward in mathematics. It's great to have a wonderfully level-headed understanding of what a definition is, but it's incredibly powerful when you have the true definition in hand and you can understand it. Now, this definition I actually include in my lectures because you're going to need it when you step into calculus, and you'll be ahead of your fellow students if you already know it. And it's a pretty easy definition. So mathematically, a neighborhood about a value A, called the center of the neighborhood, is the set of all points within a specific radius of A. Now that's a very simple definition. If you think about it, I have some point A, and a neighborhood centered at A is just a set of points symmetrically placed within some distance of A. So this might be A plus, let's use the letter delta, and A minus delta. A neighborhood centered at A is the set of all points equidistant away from the center A. So A minus delta to A plus delta. It's basically an open interval is what you would consider, and the center of that open interval is A itself. You've dealt with open intervals all the time in algebra. When somebody says, hey, could you please graph the interval from 1 to, let's just say 3? You would say, yeah, sure. What you're really graphing when you do that, from 1 to 3, is you're graphing a neighborhood centered at 2. Now, the thing you need to understand about neighborhoods is that they're all open on the edges. So a closed neighborhood is not what you're going to work with in calculus. So don't worry about that. But the language is important. And I'm not teaching you this just to throw it out in the next slide or something like that. You will need this when you move forward, and I'm going to use this in some of my lectures. So it's good just to know if I say, hey, I've got a neighborhood of radius 1 centered at 5, you know that's going to be some open interval centered at 5 with radius 1. In other words, it goes down to 4 and it goes up to 6. That's the radius of 1, right? 5 plus 1, 5 minus 1. For example, the neighborhood of size 3 about the point A equals 1 is the interval from negative 2 to positive 4. Let's go ahead and illustrate this using an interval, specifically a graph of an interval, to get a better idea of the definition. Now, we've already done this. It just happens to have been printed as my next slide, so I'm just doing this. So we have a center at 1, and we're saying the size of the neighborhood is 3. So I'm going to wiggle to the right by 3 units. That'll get me all the way over to 4. And I'll wiggle to the left the same distance, 3 units. And that will get me all the way over to 1 minus 3 or negative 2. And this, my friends, is the neighborhood centered at 1 of size 3. Even though technically the size of the neighborhood is actually, the distance from left to right is actually 6, we call it a size 3 neighborhood because its radius is size 3. As an aside, the word neighborhood is so theoretical in mathematics that it's usually reserved for upper division math students. But it's such an easy concept. You just have a center at A equals 1 in this case, and a radius away from that center. And by the way, neighborhoods don't need to be two-dimensional. You could say, I have a neighborhood about the point in space right here, and that neighborhood is of size 2. for example. So I just draw a ball, is what we'd call that. Draw a ball in space. And I'm going to illustrate that it's 3 dimensions. So there's a sphere. And like I said, it's of radius 2. Now, because it is a neighborhood, technically, I shouldn't have all the edges of that ball be solid. I would have them dashed or something like that all the way around. And then you would get this beautiful neighborhood of size 2 about that point in space. And by the way, even further, by the way, I suppose, is that these arguments go into n-dimensional spaces. So you can have a point in 12 dimensions and it could be the center of a neighborhood of size 4 or something like that. Now, why do I have all this conversation about neighborhoods if you're not going to see something like that unless you go into advanced mathematics? Well, it's because you do actually see something like that. You're heading towards calculus if you're in pre-calculus or college algebra, so that means you're going to hear the word neighborhood once you hit calculus, if you have a calculus teacher worth anything. If they're worth less, you'll never, ever hear the word neighborhood. So before I read out these definitions, I'm going to give you a layperson's version of this definition. You have a curve. It might look something like that. And let me actually go ahead and put a solid dot there. And actually over here, I'll say that's an open circle. So let's just pretend that's our function f. This point, this tippy top point up there, is considered to be a local maximum. Shorthanded, that's just local max. And in fact, I often write that as L max. It's called local because if you look to the left and to the right, the function both exists on either side of it. That's pretty important, actually. And the function it drops on either side of that point. So locally, that is the highest point. Now, if I zoom out, let's change this function very slightly because I want to make a point here. Now I'm going to zoom in and talk about this dip right here. The lowest point at that dip is called a local min, which I'm going to just say is L min, but locally, that's the local min. And I say locally because, again, if you're standing right there and you look to the left and you look to the right, the function exists on both sides and it's the lowest point. In other words, on either side, the function is rising up from that. So that's a local min. If I zoom out and go to this next peak, again, that peak right there is called a local max. Notice it is not actually taller than this local maximum. That doesn't matter. It's called a local max if when you zoom in enough, it is the highest point locally. And if I've zoomed in this much, definitely it is the highest point locally. The function exists on both sides and the function drops on either side as well. Finally, kind of the obvious one as well, dropping down here, this locally is a minimum. So without giving you the definition, it's pretty easy to understand, at least at this level, what a local maximum and a local minimum are on a function. However, each time I illustrated what a local max or a local min was, I said something that you should have paid attention to. The thing I was saying every single time was the function exists both to the left and to the right. Well, if I go over to this point right here, this point cannot be a local maximum, even though if you look to the left, the function drops. It's because of two reasons. One, if you look to the right, the function doesn't even exist. So the function has to exist on both sides for it to even be a candidate for a local max or a local min. But the second real reason here is that this is an open circle. The function isn't even defined at that point. So because the function is not defined at that point, it can't actually be a local extreme, local max or a local min. Let's go to the other side where the function is defined at the edge, right over here. Let me make sure it looks like it's defined. Now, some people would say that's a local min because it's a low spot on the function, but it's not true. If you look to the right, definitely the function is above. But if you look to the left, the function doesn't exist. And if the function doesn't exist on one side of a point, that point cannot be a local max or a local min by definition. So speaking of definition, let's actually take a look at the official definition so I can sneak in some rigor into this conversation. Again, if you want to go into calculus, this is where you're heading. The function f is said to have a local maximum, so again, the highest point locally, also known as a local maximum value. It has a local maximum at some point a if f at a is greater than and oddly enough or equal to, that's a weird condition, but greater than or equal to f of x for all x, and here's the critical piece, in a neighborhood centered at a. That phrase neighborhood, or that word neighborhood about a, means that you have some open interval centered at a. Not only is it an open interval centered at a, but the function exists on that open interval centered at a on both sides. That's the critical piece. So this, bringing it down here, if you take a look at the function, our function does not exist on the left-hand side of this point. So if that point occurred at, let's just pretend x equals 1, if I created a neighborhood about x equals 1, the function exists for all those x values, but it doesn't exist for these. And so this point cannot be a local max or a local min because that point is not the center of an open interval that the function is defined upon. It's a very tricky definition, but basically it boils down to this. The function has to exist on both sides of the point for the point to even be considered as a candidate for a local minimum or a local max. If it's the edge point of an interval and the function doesn't exist on the other side, you can just not even look at it. It's not a local extreme. Finishing out the definition, that function is said to have a local minimum or a local minimum value at a if f of a is less than or equal to f of x for all x, again, in a neighborhood centered at a. So let's see if we can use this definition. We're going to hop over to Desmos and graph the following function for a equals 1 and b equals 1. And we're also going to play with different values of a as well. But we're going to talk about local maximums and local minimums. We're also going to talk about where the function's increasing or decreasing. So we get to kind of play around with this and really pull in the idea of local maximums and minimums and increasing and decreasing into a very robust example. Let's go ahead and go over there. We're going to start by remembering that they required us to limit our window to be between -10 and 10 in the x direction and in the y direction from -10 to 5. So to do that, we just click on the tool icon and then go down to the y-axis here, and we're going to change that to go from -10 to 5. After doing that, I just click off that screen and I'm going to go over to the left-hand side and enter in the function. When you're done entering the function, first of all, I want you to notice I actually put spaces in my function quite a bit, mainly because I want to avoid the possibility of Desmos thinking that I'm creating a function named ALN. Instead, I leave a little space there. I think that you could actually not have put the space in there and you'll be fine. Same thing inside the sine function here. I have sine of bx and I put a space there. Desmos should be okay if you don't have the space, but I'm just letting you know a space is not harmful to put in there. The next thing I need you to notice is that because a and b are called parameters, these are values will change on the fly. They're not variables, they're just values that we get to modify. Desmos is going to ask us to add a slider for those. And so I'm just going to add a slider for all of them at once. And notice it automatically starts us with a equals 1 and b equals 1. Now our goal in this problem really was to state at least one interval over which the function is increasing and another one over which the function is decreasing. And we needed Desmos for this because you would not be able to find this out without calculus. So you can see, and I'm gonna just destroy my zoom level by zooming in, you can see that the function is actually increasing from this point up to that point. It's rising from left to right. That is, for any two x values within this interval from -7.724 all the way up to -4.917, as long as one x value is less than another x value, the function value at the first x value should be less than the function value at the second x value. So in this case, we could say the function is increasing on the interval from negative 7.724 all the way to negative 4.917. And that's how you would write the interval over here on the left-hand side. Notice I use open parentheses. So intervals of increase and intervals of decrease never include their edge points. So that's just something to note. You can also easily state intervals of decrease here. And in fact, I'm going to choose a very interesting interval of decrease. I'm going to say that the function is decreasing from negative 4.917, that's the x value, all the way up to x equals 0. Now I want to showcase this. The function is definitely decreasing. It's like you have this ball that's rolling down this hill, and it continues to roll down this hill as you get closer and closer to x equals 0. It just drops down forever and ever and ever. So again, as an interval of x values, I would write that as the open interval from negative 4.917 to 0. That's where the function is decreasing. So we have that the function's increasing on this first interval and it's decreasing on that second interval. You can also say the function is actually increasing from 0 all the way up to, or I should say x equals 0, all the way up to x equals, what is this, 2.074? So there's a lot of intervals. If you zoom out, there are a lot of subintervals where this function is increasing and decreasing. It's decreasing, then it's increasing, then it's decreasing, then it's increasing. So you get these little switch backs. It's switching back and forth between increasing to decreasing over and over again. Now, part of the question was also asking us to state all local extrema, local maximums, and local minimums on the given interval. So let me go ahead and go back to our given interval. To do so, I just go ahead and type back in here x going from negative 10 to positive 10. I don't really need to change the y values because I can see where we have local maximums and local minimums. I'm going to click off of this or hide the expression list, and you can see that at least on this interval, Desmos will automatically anchor to the local maximums and local minimums. So each of these is either a local max or a local min. For example, negative 7.724, 1.053, that's a local minimum because to the left and to the right of that point, the function exists, and it's the lowest such point locally. If I zoomed in there, it would be the lowest such point. Negative 4.917, 2.572, yeah, that is a local maximum. Again, the function exists on both sides of that point, and locally, it's the highest point. And you can see we have two more local maximums, one at 2.074, 1.606, and another at 7.98 and 3.069. And then we have one more local minimum at 4.488, 0.526. What really throws people off is that they think that there's a local minimum somewhere down here at the bottom of our screen, but that's actually not true. If you were to say, for example, negative 15 was the local minimum, I would argue against that because I would say, well, the function actually goes below that. In fact, the function goes as low as I want it to go because it dives down to negative infinity. It keeps falling forever and ever and ever. So that's kind of the discussion of local maximums, local minimums, and then intervals of increase and decrease. I just want to showcase as well that you can change values of A and B here. And so this is how you would play with parameters in Desmos to get really kind of neat looking pictures. You can do this all day long. It's kind of fun, actually. That's the only reason why I included that question about fiddling with A and B, just so that you know that you can do that and get brand new local maximums and local minimums. When you adjust these values, for example, A is the amplitude of the natural logarithmic function, or that term that involves the natural logarithm. And this is just kind of fun to play with, that you can see the amplitude of our function, or at least the y values, change as I adjust this. Likewise, if I were to change the value of b, well, that changes the period of the sine curve. So these wiggles, they occur faster if I increase b, and they are slower if I decrease b. And just to let you know, in Desmos, you always have the opportunity to play around with animations. And so you can click play on this animation. And let me go over here and I will go ahead and turn this down and I'll click play on that animation. So you can see two things happening at once. In fact, it might be nice to have them at two different speeds so you get a kind of a different view of things. But this is something I encourage you to play with in Desmos to really figure out what parameters do to graphs of functions. In this case, this is a very complex function, but in the long run, it's always fun to play with this stuff. So I highly recommend taking your time and take advantage of Desmos because it does have some beautiful properties where you can graph parametrized functions like this. All right, that's enough for this video. That's all I'm going to do in this video. So I hope that helps out. Again, it was pretty much just a focus on how to use Desmos to help visualize functions, but we did take time to talk about increasing and decreasing intervals and also to talk about local maximums and local minimums. I hope to see you in a video in the future. Have a great day.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way, cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Says, listen close, don't talk too much that isn't kosher. You may really hurt inside. It doesn't justify you to speak too loud and cry.